Hi, in this video, I am going to go through the AQA A-level Chemistry paper. This is paper 1. This is the 2019 paper. And it's the second half of paper 1. I covered the first half in an earlier video. So this is the 2019 paper. Okay, so this question refers to an early paper. Suggest 2 ways the student could reduce the percentage uncertainty in the measurement of the volume of thiosulfate. And in the previous question, which I really should have stopped the video in the wrong place, you had thiosulfate in the burette, and you had an iodine solution in the conical flask, and you're doing a titration, and the titer was 9 centimeters cubed. Now that is too small really to be accurate. You usually aim for, because the percentage error is going to be smaller, you usually want about 25 centimeters cubed to reduce the percentage error in the measurement. So what could we do in this experiment to make sure that instead of getting 9, we get 25? Well, you can make the thiosulfate more dilute. If you make it more dilute, you're going to need a greater volume of it. To make it about twice as dilute, you need 18 centimeters cubed. You'll halve the percentage error. The other thing you could do is, so that you need more thiosulfate, the second thing you could do is you can make this iodine more concentrated. That means you'll need more thiosulfate. So you want more moles of iodine in the flask there. So they quite regularly ask that question. You've got to recognize that, really you want 25 centimeters cubed for a titer to get a reasonable percentage error. And you've got to change the concentrations of the other two things to make sure that your titer is big enough to give you an accurate result. Okay, state the role of iodine in the reaction with sodium thiosulfate. Now, you've got to think acid-base reaction, redox, something like that. Well, hopefully you realize this is a redox reaction, because look what happens to the oxidation number of iodine. Here the oxidation number is 0, and here it is -1. The iodine gets reduced. In other words, the iodine itself is acting as an oxidizing agent. Right, what is it oxidizing? It doesn't ask you that, but it's oxidizing the sulfur in thiosulfate. If you work out the oxidation number of sulfur in thiosulfate, it's 2. In this, strangely, it's a fractional value. The oxidation number there is 2.5. So you've oxidized the sulfur, and the iodine is the oxidizing agent. Okay, I've included a bit of the periodic table there because we've got to give the electronic configuration of a copper 2 ion. Right, the first thing I'm going to do is give the electronic configuration of a copper atom. Let's do that. So we're going to have 1s2. The 2s2 is full up, of course. 2p is also full up there, 2p6. 3s is full up, 3s2. 3p is also full up. Now we move on to the last bit, which is the important bit. We have a full 4s. So that's 4s. Well, we think you'd have 4s2, but we'll see in a minute. And you'd think you'd have how many in the D? 1, 2, 3, 4, 5, 6, 7, 8, 9. 3d9. Of course, you probably remember that that is not 9. So it has a full shell. You get 3d10, and it sort of takes that one out of 4s1. But we want the copper 2 ion. So where are the electrons lost from? Well, you lose the electrons from the 4s. Always you lose the electron from the 4s, and then you're going to have to lose 1 from the 3d, so that is going to be 3d9. So that is the electronic configuration of the copper 2+ ion. Copper 1 iodide is a white solid. Explain why it is a white solid. Well, if it's copper 1, look, this is copper 2. We have got here, we've got 3d9. So copper 1, you're going to have blah, 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 3d9. D10. Right. Now, the reason why it's white is because the D shell is full. Let's write that down. The 3D shell is full. So that means there's no, you can't have any transitions from one D shell, one D orbital to another. And with transition metals, it's the reason why they're colored in the transition metal ions are colored is because they absorb visible light to actually promote electrons from one d orbital to another. Well, that's not possible here because it's full up. Okay, so copper 1 iodide is a white solid, just like zinc. All zinc compounds are white or colorless because they've got a full D shell too. Okay. Right, now here's an ideal gas calculation. Right, we have to remember here to be a little bit careful here that iodine is I2, so the atomic mass of iodine, AR, is 126.9, but the MR of I2 is going to be double that, is going to be 253.8. So that's a bit of a common mistake. People forget that iodine is a diatomic molecule here. Right, we've got to calculate the volume of that of 5 grams of iodine vapor using the ideal gas constant. Okay, so we're going to use PV is equal to nRT. Rearrange that to get the volume we want, which is going to be equal to nRT nRT over P. Now, N is the number of moles, okay? The number of moles of iodine, we've got to find that out from the mass. So let's do that. N moles of iodine is equal to the mass over the MR. The mass is 5 grams. The MR is 253.8, which is equal to 0.0197. So now we have to put our numbers in there. Right, now we've got to be careful here. They ask for the volume in centimeters cubed. This expression is going to give our volume in meters cubed, and we're going to have to convert that afterwards. Okay, you always have to be really careful with units. The ideal gas equation. Let's talk about what else we need to do. That 100 kilopascals, that needs to be in pascals, so we need 100,000 pascals. The temperature here, that needs to be in kelvins, so 185, you add 273, so the temperature is in Kelvin is going to be 458 Kelvin. Okay, so let's put the numbers in. V is equal to the number of moles, 0.0197, multiplied by the ideal gas constant, multiplied by 458, divided by the pressure in pascals, 100,000. That gives us an answer of 7.497 times 10 to the minus 4, and the units of that are going to be meters cubed. Right, how many centimeters cubed in a meters cubed? There are 10 to the 6 centimeters cubed in 1 meter cubed. So we're going to multiply that by 10 to the 6. So that gives us a final answer of 749.7 centimeters cubed. Give your answer to 3 significant figures. Well, that gives us 750 centimeters cubed. As I say, the main mistake people make there, I think, is forgetting that iodine is diatomic, and so they get double the volume you'd expect. Okay, right. Now we've got a question on equilibrium. Okay, we've got sulfur trioxide decomposing. A sample of sulfur trioxide was heated and allowed to reach equilibrium. The equilibrium contained that many grams of sulfur dioxide, and we've got to calculate the mass of oxygen in the equilibrium mixture. Right, so we need to think of working in moles here, and grams is no good to us really. So if we've got SO3, and that's going to give us that. So if we produce X moles of SO2, we're going to produce X over 2 moles of oxygen. Right, let's work out what this value X is. Okay, so moles SO2 produced, X, is equal to the mass we've got divided by the MR of SO2. Right, the mass we've got 6.08 grams. The MR of SO2 is 64.1. So that works out to be 0.0949 moles. Sorry, 949. Okay, so we've got that many moles of SO2. So the moles of oxygen, we've got to divide that by 2. So the moles of O2 is equal to 0.0949 divided by 2 is equal to 0.0474. The question asks us to work out the mass of oxygen in grams in the equilibrium mixture. So mass of oxygen, you've got to multiply by the MR. Mass O2 is equal to moles times MR. So that's 0.0474. Now the MR of O2, so O2, don't forget, is 2 times 16, 32. So that is going to be 1.517 grams. We should really give it to 3 significant figures because that's the 3 significant figures there. So that's 1.52 grams. Okay, so carry on with this question then. They will say a different mixture now, in case you didn't get that bit right. A different mass of sulfur trioxide was heated and allowed to reach equilibrium. Okay, the amount of each substance in the equilibrium mixture is shown below. So there's the moles of each one here. They give us the value of Kp. Calculate the mole fraction of each substance, then write the expression for Kp and work out. So let's work out the mole fractions first of all. So the mole fraction, right, mole fraction, quite often use that little symbol lambda. Okay. Now just to remind ourselves that mole fraction is equal to the moles of the thing you've got. Mole fraction of, say, A is the moles of A over the total moles. Well, what's the total moles we've got here? The total moles is going to be 0.32 plus 1.2 plus 0.6. That is equal to 2.12. Okay, so now to work out the mole fraction for each of those things here, let's do that in red here, up here. What I've got to do is got to do the moles divided by the total moles, which is 2.12. So if I do 0.32 over 2.12, I get there 0.151. This one, 1.2 over that, we get 0.566. And mole fraction of oxygen, 0.283. And a quick check, if you add those up, they should equal to 1, of course, and they do. Okay, so that's all fine. So we've done the first part of that. Give an expression for the equilibrium constant Kp. All right, before we do that, I'm just going to write down what is going to be the partial pressure of each thing. Now, just to remind you, partial pressure, are usually given that symbol of A, is equal to the mole fraction of A multiplied by big P, where big P is the total pressure. Okay, and that's what we've got to find out in this calculation. So I'm going to put down here in this table, first of all, I'm going to rub that out. I'm going to put down the partial pressure of each thing. So that's going to be 0.51 P. That's 0.566 P. And that's 0.283 P. Okay, now we need to give the expression for Kp. I'll clear a bit of space here. Right, the expression for Kp, right, this equation, just look at the form of the equation, we've got, okay, mess that up. Better, right? We have got the expression is, how I wrote it down, is SO2SO3 goes to 2SO2 and O2. So Kp is going to be equal to the partial pressure of SO2, and that's going to be squared the partial pressure of oxygen, and that's just going to be not squared because there's no number in front of the oxygen, divided by the partial pressure of SO3, and that's going to be squared as well because we've got a 2 there. Right, so now we can start putting in some values, okay, because we want to find out. Okay, so what I'm going to do is I'm going to relook at the partial pressure of each thing is equal to the mole fraction multiplied by the total pressure, okay, and so I'm going to put those values into our expression, our Kp expression. So let's do that. Kp is going to be equal to the partial pressure of SO2, which is 0.566, multiplied big P, all squared, multiplied by the partial pressure of oxygen, so that's 0.283, multiplied by big P, the total pressure, divided by the partial pressure of SO3, so that's going to be 0.151 big P, all squared. Now let's multiply that out, so we get Kp is equal to 0.566 big P squared times 0.283 P divided by 0.151, sorry, that should be a squared there, squared big P squared. Right, we can do some cancelling out here. We can cancel out that P squared and that P squared, which makes life a lot easier. I'm going to put in the value for Kp now. Now Kp, they tell us, is 7.62 times 10 to the 5. So let's do that. 7.62 times 10 to the 5 is equal to 0.566 squared over 0.151 squared multiplied by 0.283 big P. Rearrange all of that to get big P all by itself, the total pressure, which is what we're trying to find out. Big P is going to be equal to 7.62 times 10 to the 5 multiplied by 0.151 squared divided by 0.566 squared multiplied by 0.283. Okay, and work all of that out, and we get 191,700 641, and the units are going to be in pascals because all our partial pressures are in pascals. We need to give that to three significant figures because that's the data given to three significant figures. So that's 192,000 pascals. That's our final answer. Okay. Now, right, this is asking us about changing the temperature and the effect on the position of equilibrium. Okay, right, I'm just going to copy that expression for Kp, I think. Okay, I'm going to copy all of that. Okay, so we've got this equation here as well, but let's just, okay, now we look at this, okay, this box here. Right, at a higher temperature, so at higher temperature, Kp is bigger. Now, if Kp is bigger, it means we've got more of this on the top, okay, and less of the SO3 on the bottom. So that means the equilibrium at higher temperature is pushed that way. The equilibrium moves right at high temperature. Okay, now Le Chatelier tells us if you increase the temperature, it tries to decrease the temperature by moving the endothermic direction. So this forward reaction is endothermic. 2 marks, that is a lot of explanation for that. You probably don't need to be quite as clear as that, but there you go anyway. So basically Kp gets bigger, this number on top gets bigger, you get more products. It must be moving the endo direction. Right, okay, now here is another question, and this shows the importance of when you talk about Kp, you've got to write down the equation. Without writing an equation, Kp is a bit meaningless because when you write with the question this way, okay, the Kp value is that, but they haven't written the equation that way. They've written it, first of all, they've written it well in the same direction, but they've used halves instead of balancing it by using 2's. So if we, and what's it's going to ask us, it's going to find out the value of Kp if you express the equation like that. So let's write down, let's call this Kp dashed. Okay, so the expression for Kp dashed is going to be the concentration of SO2, not squared, sorry, not the concentration, the partial pressure of SO2, not squared, multiplied by the partial pressure of O2 to the power of a half, or in other words, the square root of partial pressure of oxygen, divided by the partial pressure of SO3. Now you can see that Kp, the original Kp, this one here, I'll do this in green, I won't call it Kp dash, just Kp, that is SO2 squared times that partial pressure of SO3 squared. So you can see this new blue Kp, the Kp dashed, is actually the square root of the original Kp, the green Kp. So Kp dashed is equal to the square root of this one, green Kp. Let's put the numbers in. The value, that's 3.94 times 10 to the minus 4. That works out to be, the square root of that is 198.4849. Let's do to three significant figures, 198. Now, what are the units of that? Well, let's look at the units of this blue equation up here. Well, the units of Kp are going to be the same as the units on the right. So what have we got on the right? We've got the we've got pascals for the SO2. We've got pascals to the half, power of half for the oxygen. And we've got pascals for the SO3 on the bottom. So those two pascals cancel out. So we end up with units of pascals to the half. Okay. Again, it shows you the importance of when you state, a value of Kp, you've got to give an equation with it, because otherwise it's ambiguous. Okay. Right. Structure and bonding. Now, draw a diagram to show the strong interaction between two molecules of ethanol in the liquid phase. Right. Now, ethanol, you can probably tell before I start drawing it, it can form hydrogen bonds. Okay, so let's draw an ethanol molecule. So I'm going to draw why can it form hydrogen bonds? Because we have got this proton here, strong partial positive charge on it because it's connected to the very electronegative oxygen. I'm putting the partial charges. Oxygen, of course, has got two lone pairs. Draw two there. And one of those lone pairs can form an interaction, the hydrogen bond interaction with the hydrogen on another ethanol molecule. Let's do a different color. Okay. I just draw that one like that. That will have two lone pairs on it as well. Delta positive, delta negative, and delta positive. Okay, so that's hydrogen bonding between two ethanol molecules. Okay. Fairly standard question, but you've got to realize, of course, that it is hydrogen bonding. Okay, now methoxymethane is an isomer of ethanol. Now that can't form hydrogen bonds, and that's what this question is all about. Okay, so it gives you the boiling points, and in terms of intermolecular forces, explain the difference in the boiling point. So I think we need to say for methoxymethane, let's just draw it. There's no possibility of hydrogen bonding there because there's no H bonds, because there's no hydrogen attached to an oxygen. Okay, so there's no hydrogen bonds. What kind of intermolecular forces can you get there? Well, you can get probably dipole and van der Waals forces. No, they don't tend to really care whether you say van der Waals or dipole interaction, so I'll just say van der Waals. Okay, so in methoxymethane, you only get van der Waals forces, and these are much weaker than H bonds. And this 3 mark here, I think they nearly always ask you to say, they usually ask you, there's a mark for saying something about the energy required to break them. So they're much weaker, so less energy is required to overcome them. So the melting point of the boiling point of methoxymethane is a lot lower than for ethanol, again, because ethanol does have H bonds. Okay. I think in that question, you're probably getting 1 mark for saying van der Waals, 1 mark for saying they're much weaker, and 1 mark for saying the energy required to break them, therefore, is a lot lower. Right, shapes of molecules now. Okay, draw the shape of the POC3L molecule. Okay. Name each shape, and then we've also got the ClF minus ion. Let's just do POCl first. Okay, so right, so that is going to be like this. Which group in the periodic table is phosphorus in? It's in group 5, isn't it? So it's got 5 electrons in its outer shell. Now it's going to be using 1 electron in that bond, 1 electron in that, 1 electron in that, and it's going to be using 2 electrons in the double bond. So that's all 5, so there's no lone pairs. With a double bond, we just treat that as a single bond when we're using shapes of molecules. So if essentially we've got 4 bonding pairs. Whenever you have 4 bonding pairs, you get what is the shape is going to be tetrahedral. Let's see, what does it ask? It says name each shape. Right. Draw the shape of the molecule and include any lone pairs. So I think we need to draw the shape. So I'll draw a phosphorus there. We have got a double bonded oxygen there. We've got 1 chlorine coming out of the page, 1 going in, and 1 in the plane of the page. That's a tetrahedral molecule. There are no lone pairs to cause any distortion there. Now we need to transfer our attention to the ClF4 minus ion. Now we need to worry about lone pairs there. So I'm going to, right, so let's ClF4 minus. Right, I'm going to draw a chlorine here, and you're going to have 4 fluorines attached. This isn't part of the answer, this is just working out. You don't draw a dot cross diagram, but I'm going to just draw it. Now, chlorine is in group 7, so it's fluorine. So you're going to have 4 single bonds here. Right, I've only drawn the electrons of the chlorine, but the fluorine, each fluorine is going to have 3 lone pairs. Yeah, don't worry about that. That's not really important in the shape. But the chlorine here, now I have drawn 4 dots for the chlorine. Chlorine is in group 7. So I've only drawn 4 of the 7 electrons. So I need to draw 3 more. 1, 2, 3. But this is ClF4 minus, so there's an extra electron which is taken somewhere else. There it is. Okay, so we can see what we've got here is we have got 4 bond pairs. And we've got 2 lone pairs. That's a total of 6 pairs altogether. So the basic shape would be octahedral. Right, let's just see exactly what the question asks. Does it ask for a diagram or does it just ask for a bond angle? Let's see here. Draw the shape, and we've got to draw the shape of this one as well. Okay, and we've got to suggest a bond angle value here. So let's do that. So we've got octahedral is the basic shape. So I'm going to draw chlorine here. We're going to have 2 pairs of electrons going in. So that pair of electrons going into the plane, these ones coming out. And then you have 1 sticking up and 1 sticking down. Now, I'm going to put my fluorines here. So that means we're going to have 2 lone pairs, 1 there and 1 there. Put it like that if you like. Okay. Now, that's good for the shape. So we'd actually call that shape, we would call it square planar. What is going to be the bond angle? Well, the bond angle normally here is everything is 90 degrees in octahedral, isn't it? And it will be 90 degrees because if you like, this lone pair is going to distort it, trying to push the fluorines down that way. This lone pair is going to try and push them up so they cancel each other out. So the bond angles will remain 90 degrees. So that is that question answered. Again, this, don't cross that out if you draw it. You don't want them to mark that. That's just working out. Okay, on to a question about pH and acids. Okay, right. For pure water, the pH at 40 degrees C, the pH is 6.67. A student thought the water was acidic. Explain why the student is correct and determine Kw. Well, we have to know that Kw is equal to the concentration of H plus ions multiplied by the concentration of OH minus ions. We know that. And we know for any neutral solution, the concentration of H plus is equal to the concentration, of OH minus. Right, so why, the first part then, why is the student incorrect? The student is incorrect because H plus concentration is equal to OH minus concentration. That's why he is incorrect. All right. We've got to determine the Kw. Right. For this, and this is the case when it's neutral, when H plus is equal to OH minus, Kw is equal to the concentration of H plus squared. Okay. Now we know that the pH is equal to 6.67. So that means the H plus concentration is equal to 10 to the power of minus 6.67, which is equal to 2.138 times 10 to the minus 7 moles per decimeter cubed. Right, so let's work out Kw at this temperature then. Kw is equal to that squared, 2.138 times 10 to the minus 7 all squared, which gives us 4.57 times 10 to the minus 14 mole squared dm to the minus 6. And you can see here why the value Kw at 298 Kelvin is 1 times 10 to the minus 14. Well, we can see here it's gone higher. Okay, it's gone higher here because the temperature isn't 25 degrees C, it's 40 degrees C. Incidentally, that means the equilibrium, more of the water splits up, and that would tell you that the splitting up of water is endothermic. They quite often ask that as well. They're not asking it here, but they quite often do ask that. Okay. Right, now we have got this question here. All right. Now we have got sodium hydroxide, which is a strong base, and it's been titrated against propanoic acid. That's a weak acid. That's pretty important. Right. And there's our titration curve. Okay, so here's the volume of NaOH on the x-axis, sorry, and the pH here on the y-axis. Use figure 4 to determine the value of Ka, okay, and show your working. Right. Now, what they're asking us to do here, there are a couple of ways of doing this, but I think really what we need to be looking at half equivalence point. That's the easiest way of doing this. Now, we know that Ka for weak acid, Ka is equal to H plus A minus concentration divided by HA. Okay, now let's see what happens during neutralization. We've got HA plus OH minus goes to A minus and H2O. Right, if we add 1 mole of that and a half equivalence, we'd only add half the moles of that, 0.5 moles of that, but not of that. So start and then final, we would end up, you can see there, we'd end up with 0.5 of a mole of HA and we'd have 0.5 of a mole of A minus as well. Now, if you do that, the concentrations of those two things, of HA and A minus, that one and that one, they're equal. A minus is equal to HA. So what happens is they cancel out of the expression. So we're going to get rid of that, get rid of that. So you can see there, write it here, Kw, sorry, Ka, at half equivalence point is equal to H plus. Let's take logs of both sides of the equation there. We end up there, minus log of base 10 of both sides. So minus log of Ka, that's equal to pKa. Minus log of H plus is equal to pH. So we can see at equivalence point, pKa is equal to pH. Now we're at half equivalence point, sorry. Right, you don't need to write all this down. This is just explanation. So here is the equivalence point. The equivalence point is there. That is 19.2 centimeters cubed. So that means half equivalence point. That's going to be half of 19.2. Which is 9.6 centimeters cubed. So we need to find out where's 9.6. It's about here. Okay, so we know we're going to extrapolate that line up, extrapolate that line across. I've done it very carefully. That's about 4.9. We can see there that because at half equivalence point pH, pKa is equal to pH, we can say that the pKa here is equal to 4.9. So what's Ka is equal to 10 to the minus power of 4.9, which is equal to 1.26 times 10 to the minus 5. And the units are going to be mole per decimeter cubed. Okay, so you find the Ka from the half equivalence point there. There is another way of doing that, calculation. They obviously want you to do it this way because they're giving you a titration curve, but you can actually do it from looking at the initial pH. Okay, I'll just do this now just to show you, you get the same answer, more or less the same answer. Okay, so let's say the start pH. Again, you don't need to do this to get any of the marks. Just the start pH is equal to, that's 2.9. Okay, the start concentration of our propanoic acid, it tells us in the question is, what was it again? 0.08 moles per decimeter cubed. Now, we know that, I'll just write it in here, we know that Ka is equal to H plus A minus divided by HA. So what we could do here is we know at, in this case, for every because what happens is the acid dissociates, HA gives you A minus and H plus. The concentration of H plus is going to be equal to the concentration of A minus at the start, because all of the A minuses come from dissociated HA. Okay, so we've got that. Now H plus, we can work out the concentration of that because we know the pH. That's pH is 2.9, so that's 10 to the power of 2.9, which is equal to 1.26 times 10 to the minus 3. Okay, now what else do we also know? We know that, right, HA is equal to 0.08. Now it won't quite be that, it'll be a tiny bit less because some of it is dissociated, but it's going to be approximately equal to that, so we can use that value in the expression, no problem. So let's put our values into this expression, that value and that value there. Okay, so we're going to get 1.26 times 10 to the minus 3 squared, because the concentration of HA is equal to A minus, and divide that by 0.08, and that gives us an answer of 1.98 times 10 to the minus 5. Okay, now it's not exactly the same as that one there because I haven't read the values very accurately off the graph, but it would, if you did work it out that way, so it's just mole per dm cubed, you would get all the marks. If you look in the mark scheme, it says so. But what they really want you to do is use the half equivalence method there. That's why they give you the graph. Okay, which indicator is most appropriate for the reaction in 9.2? Right, let's look at this. This is looking a bit of a mess now, but we can see here, we need our indicator to change color in this bit of the graph. Okay, so we want to change it between 6.5 to 11.5. So you want an indicator that changes then. So I'll just put that 6.5 somewhere to 11.5. Right, this one is way too low. This one's a little bit too low. This one would be good. This one's too high. So go for the cresylphthalene. That would be the best indicator there, because it's changing in that range. Okay, now here is a buffer question. This is a 6 marker and it's a tricky one. Okay, so right. Right, okay. So what we've got this the weak acid HX and its salt, potassium X. Right, and they make a buffer by mixing the two together, but then they add a little bit of potassium hydroxide to the buffer solution. Okay, now we've got to calculate the pH of the buffer. Now, whenever we do a buffer calculation, I always rearrange this expression to make H plus the subject of it. So we know that H plus is going to be then equal to Ka multiplied by the concentration of HA over A minus. Okay, so the pH of the buffer is dependent on two things. Well, the H plus concentration is dependent on two things. It's dependent on the value of Ka, and it's dependent on the value of this ratio of the weak acid to its conjugate base. All right, so we need to fill in these, and Ka they give us, but we need to find out what this ratio is here. Okay, so what makes this a bit, so let's work out the initial moles of each thing then. Okay, let's say the start moles of HX. How do we work that out? Well, we've got the concentration and the volume. Okay, conc times volume, so that's going to be 0.1 times 0.5 is equal to 0.05. That's the start moles of HX. The start moles of the salt, they just tell us, is 0.136. Makes life easier. So start moles of X minus is 0.0136. The potassium's not doing anything there. But then we also add a small amount of potassium hydroxide, okay? Right. Now, which one of these is potassium hydroxide going to react with? Is it going to react with HX or with X minus? Obviously, it's going to react with HX. So let's write down an equation there. We're going to have HX plus OH minus, and that's going to react to form X minus and water. I'm going to write down here the start moles, the final moles of each thing, and then the final concentration. And those final concentrations I am going to use to put them into here to work out H plus. So let's do the start moles. We know that is 0.05. We worked that out. The moles of OH minus is 3 times 10 to the minus 4, 0.0003. The start moles of X minus, 0.0136, and we don't care about water. Okay, we'll ignore that. Now, how much HX is going to be left over at the end? Well, it's going to be 0.05 minus 0.003, which is equal to 0.0497, What's happened to the moles of X minus? Well, that's going to go up, isn't it? Because an OH minus, every mole of OH minus is going to make one more of that. So that's going to be 0.0136 plus 0.0003, which gives us 0.0139. Now the final concentration, well, we've got the number of moles, well, we've got to divide by the volume. Okay, we don't know the volume because they don't tell us the volume of potassium hydroxide, but that doesn't matter. We're just going to call the volume V, and we're going to divide by V, 0.0497 V, and you'll see these V's are going to cancel out. 0.0139 divided by V. Now all we've got to do is put our numbers into this equation here, right? So we're going to get H plus, make a bit of room here, do it in orange. H plus is going to be equal to the value of the Ka, which is 1.41 times 10 to the minus 5, multiplied by HA, I'll call it HX, so 0.0497 over V divided by 0.0139 over V. Those V's are going to cancel out. So H plus is going to give us, H plus is going to be equal to, I'll write this out in full, 1.41 times 10 to the minus 5 multiplied by, well, this fraction here works out to be 3.575, and that fraction is always between 1 and 10. Okay, so that's a good check to make sure you're on the right track, because it's got to be, it can't be, sorry, between, it's got to be between 0.1 and 10. That's the range it can be, because you've got to have about the same amount of HX and X minus for it to be a good buffer. Right, so let's just evaluate that, put that in, you get 5.04 times 10 to the minus 5. Take the negative log of that to get the pH. pH is equal to, give it 2 decimal places, well, it's 4.297, so you give that to 2 dp is 4.30. That's our final answer there. Okay, 6 marks for that question, and that, if you get that right, I imagine you probably get an A star. It's hard. Okay, right, last question on the paper. A buffer solution has a constant pH even when diluted. Use a mathematical expression to explain that. Well, it's only 1 mark. I would say, right, H plus, we said before, for a buffer is equal to Ka, okay, A minus. So I'm going to, what is the concentration of HA? Is equal to the moles of HA over the volume. Okay, so let's just substitute that in, and the same for A minus. So we're going to have moles HA divided by V divided by moles A minus divided by V. Right, so those V's are going to cancel out. So H plus is equal to Ka moles HA A minus. Now when you add water, you're not changing the number of moles. It doesn't change the number of moles of HA. Of HA and A minus. So the value of that fraction stays the same. So the hydrogen ion concentration doesn't change. So the pH concentration, the pH value doesn't change. Okay, that is the last question on the paper. So that's the end of that.